So today we are covering the 7.1 material that's working with the greatest common factor by working with some also factoring by grouping mixed in here as well. So the main overarching idea of what is factoring with these polynomials. Factoring is undoing the simplification process that we did in chapter 6. So we had one or two or three or four things that are being multiplied together from chapter 6. We condensed all those down, we multiplied them together, we added, subtracted, all that fun stuff, and then we got to a polynomial final answer. This process, the process of factoring, is essentially undoing that. We're breaking it down into as many of the small parts that we possibly can and find out what factors go into making the polynomial that we started with. So have that as the overarching theme or the overarching idea in the back of your mind as we're going through 7.1, 7.2, and when you move on into using factoring in the next math class as well. So factoring just undoes multiplication. That's the general way you can think on it. So the first one that we're going to start with, the main one we're seeing for this section, is the greatest common factor. And this is the largest expression that is a factor for all of the expressions given. It should also be noted, if you're trying to figure out what is the greatest common factor, the greatest common factor cannot be larger than any of the numbers or terms originally given to us. And we'll see some examples down here with this as well. But essentially all factors, it's one of a part that a lot of people very understandably kind of get confused on. We have factors of a number and we have multiples of a number. Multiples of a number are starting at that number and counting up, getting larger. So let's say our original number is 8, just making up one. The multiples of 8 are 8, 16, 24, 32, 40, and so on. Multiples count up. Factors are all numbers that multiply together to create that number. So factors of 8 would be 1, 2, 4, 8. So factors always, the greatest common factor and all that needs to be smaller or at the very least the same size as one of the original numbers or terms given. It cannot be bigger than them. We'll see some examples of that down below here. Now the process for finding the greatest common factor, and again, this is an optional one. There are multiple ways you can go about doing this. There are some different ways I'll show you guys that I think are really helpful and some tricks with this that I think are helpful for that. But it's just an optional process that I'd recommend that you can use if you'd like to. So our step 0, this is the major optional part that goes along with this. Factor each coefficient into prime. So do that prime factorization. Write all variables with exponents in expanded form. And again, I'll show you guys where this can be very useful, but it can also be a complete pain in the butt because expanded form for some of these can get really, really gross. So there's an optional step there. You don't necessarily need to do this, but I think this can help. So our actual first step, or in this process that you could use, list all numerical factors in columns for each coefficient. So that means, what are all the factors of the first number? What are all the factors of the second number? Then circle the greatest common factor for the numbers and the variables. Essentially, what is the largest number that equally multiplies into all of the numbers that I have been given? We can also do the same idea, or same thinking with our variables. What is the largest degreed term or degreed variable term in this expression or this set of expressions that can go into both the things that I've been given? There's a little bit of a trick to this one, specifically for variables, that I'll show you guys when we get into examples down here. But once we have that, we're going to bring down these common factor numbers and variables that are all expressions that all the expressions share. So you figure out what's the greatest common factor for the numbers, what's the greatest common factor for the first variable, what's the greatest common factor for the second variable, and so on. Once you have figured all of those out, you write those down for yourself. We write those as being multiplied together, like we have here in step 3. Multiply these common factor numbers and variables, all of them together, and then that will give us our greatest common factor. My recommendation, if the expression or expressions that you are factoring have coefficients and variables, find the greatest common factor of each part individually. So again, as I'm going to try and emphasize to you guys with this section, as I've done with previous ones, and I will continue doing with future ones, solve these things in parts. If you are trying to do all of them at once, it could be an absolute pain to make that happen. So work with the numbers, then the first variable, then the second variable, and so on until you have everything completed. But if you try and do numbers, variables, and keep track of it all, to me, I can't keep track of it all, so I don't expect you guys to either. So let's go and take a look at 4 examples with this, because again, I think the process it's not bad. There's a lot of ways that I've seen people go through and find the greatest common factor that isn't this method, but it's just one that we can use. And there are some shortcomings with this that I'll show you guys as we go through this as well. So we have 4 examples. That's what we're going to go through over on our Blackboard. So I'll jump us over there. We'll go through these. Okay, so our first example, and again, we're finding the greatest common factor. So our first numbers that we had are 18 and 27. So the greatest common factor. What is the largest number that can multiply into both 18 and 27? So following the process that we have listed out here, I'm going to list all numerical factors in columns for each coefficient. The idea that you could factor each coefficient into primes, that's an optional one. I'm going to go with one that doesn't have us doing that quite as much. So instead, I'm going to go with this one. I'm going to list the factor pairs of 18 here, and then the factor pairs of 27 over here. So I want to find all the factors of 18, which are all the numbers that multiply and to create it, and all the factors of 27, and then see what is the largest one they have in common. So I can list the factors of 18, 1 and 18. Oops. 2 times 9, and 3 times 6. 4 doesn't work, 5 doesn't work, 6 would work. I already have it listed, so there I go. There's my 6 factors of 18. Do the same thing with 27. Go 1 times 27. 2 doesn't work. I have 3 times 9. 4 doesn't work, 5 doesn't work, 6 doesn't work, 7 doesn't work, 8 doesn't, 9, and now I already have 9, so I'm done. So I've listed the factors of 18 in the left column. I've listed the factors of 27 in that right column that we have here. And now I want to find what is the largest factor, the greatest common factor between these two numbers. And as we're looking at it, we're noticing they both have a 9 in them. It's the largest number they both have in common. So based on that, the greatest common factor, the greatest common factor between these two numbers is 9. And then we would be done. We're going to end up later on in this same section, use the greatest common factor for some other stuff, but we need to be comfortable with actually finding the greatest common factor first. So this is a recommendation of one way you can go about, factoring these things, specifically when we have numbers showing up. List all of the factors of the first number, all the factors of the second number, all the factors of the third, and so on, until we have all those listed, and then we find the greatest one. And you can absolutely use your calculator to help you out with that if you need to. I would also recommend having your multiplication tables nailed down from everything from 1 times 1 up to at least 10 times 10, preferably 12 times 12. It's going to make this process a lot easier, I think, with finding the factors of things. But moving on, we have our second example. We have 12x squared and 18x cubed. So from here, again, we are trying to find the greatest common factor. Work with this in parts. Do the numbers first, then do the x's. So the factors of 12. Always start with 1 and the number. A lot of people forget to do that, and errors show up from that. So just like I did with the previous problem, I'm listing the factors of each of these numbers. I don't have anything beyond that. So I'm looking at this, I'm saying, okay, well, what is the greatest common factor that they both share? Well, they have 1, 2, and 3, which is great. So 3 is currently the largest if you're counting down. And see, okay, well, they also share 6 with one another. And as I'm looking down the left-hand side of both of these columns and then looking up on the right-hand side, we're seeing the numbers are increasing. So counting kind of about like this. That's the way I'm looking at these things. And I'm seeing the greatest common factor numerically is 6. Okay. So part of my greatest common factor is 6. So I have the number part taken care of. Now I need to take a look at and determine that same or very similar idea with the x squared and the x cubed. I've got to work here a little bit. So x squared, x cubed. So we've expanded each of those, each of those variable exponents out. Now again, we're trying to find the greatest common factor that these things have with one another, meaning what is the largest number that can evenly go into both x squared and x cubed? Well, the nice part about variables, there's a nice little trick with these. I'm seeing I have 2 x's here, and I have 3 x's in my second one. But within those 3, it does have 2 in it also. So what's the greatest common factor between x squared and x cubed? Well, it's going to be x squared, because they both have an x squared term within them. You could also think of this as, and I think this is the generality that helps people quite a bit, look for the variable with the lowest degree attached to it, and that's going to be your greatest common factor. So in this case, I have an x squared and I have an x cubed. Which one has the lowest degree, the lowest exponent attached to it? That's going to be x squared. And that is going to be your greatest common factor for all the x's between these two expressions. You could apply the same thinking for y and m and a and n, whatever it may be. Try up with that. Okay. So take a look at our third example with this. Okay. So listing these things out. Okay. So we got all these guys here. So finding the greatest common factor between 14x cubed, 70x squared, and 105x. So the way we're going to go about doing this, again, we want to find what is the greatest common factor between the numbers and then the x's. So again, greatest common factor, I'm going to list the factors of each of the numbers given to me. Oops. I'm trying to find what the largest one that they all have in common. So factors of 14, always, always, always start with 1 and the number. It's always going to be there. 1 times 14, 2 times 7, 3 doesn't work, 4 doesn't work, 5 doesn't, 6. Okay, so I have all the factors of 17, or not 17, 14 listed there. Now I'm listing the factors of 70. I have 1 times 70, 2 times 35, 3 doesn't work, 4 doesn't work. So I don't believe 4 works. Let's try it with the calculator. 70 divided by 4 doesn't work. 5 does work. It's a number that ends in 0. So 5 and 14. 6 doesn't work. 7 does work. 7 times 10. 8 doesn't work. 9 doesn't work. 10 works. I already have it listed. Done. And now listing the factors of 105. I'm just going to show you guys, here's a nice little trick that you can do with this. Here. Okay. So if you have your graphing calculator, now would be a good time to get that out. I'm going to show you guys a nice little trick to work with some of these larger numbers and finding the factors of them. Back to the home screen here. So, starting with the home screen of a graphing calculator, if you want to find all of the factors, or at least have some way of having the calculator list a bunch of the factors for you, there's a nice little trick in how you can make that happen. So we're trying to find all of the factors of 105. So here's how we're going to go about doing that. From the home screen, if you're not there, hit second, then mode, brings the quit option, brings you right back to the home screen. So from the home screen, we're going to go in the top left corner, we're going to go into y equals. Should bring up a screen like this. Clear out any and all other equations that you have written in there because we don't need those. So use this directional pad if need be. Lost my little highlighter here. Use this directional pad if you need to go through and select each of these and then clear them out accordingly. So you have nothing in here. Now, we want to find all of the factors of 105. So I want to find all the numbers that evenly divide into 105. So the way that I do that, under the first y equals, I'm going to type in 105, 105, and then we're going to hit divided by, right up here, the very top little operations that we have. So 105 divided by, and going to the top left, we have this xt theta n button that's in here. It's our variable button. You can think of it that way. I'm going to click on that one. So my first equation, I'm going to have 105 divided by x. And all this tells the calculator is 105 divided by, and then list all of the numbers that go into it. So we can do that. Once we have this entered in, we are then going to go into the table that is created from this and find those values. So to go to that table, we're going to click on the second option. It's in the top left corner of the calculator. So we're going to click on second. And then in the top right corner, we have the graph button. Because we have second selected, that's going to select the table option. And we'll see a table of points listed for ourselves. We want to start at the positive 1. Use the directional pad to scroll up and down to get to there. And with this, you can use this to find all of the factors of 105. Now, the big thing that a lot of people do, and this is not something that you should be doing, is they will list 1, 2, 3, 4, 5, 6. They will list every single one of these numbers and every single one of these numbers, which we do not want to do. We only want to list the whole numbers that show up. So 1 and 105, 3 and 35, 5 and 21, 7 and 15. I don't think we have any others. Yeah, we get to 15, we're back at 7 again, so this would cycle back to itself. So you guys would have this on, you could write it out in your calculator, and then as you're going through and reading this table, then just list, again, just the whole number, one versions of these, that work for the factors of 105. So I'm going to leave this up for a second here for you guys to take a look at, maybe write anything down for yourself. So we'll jump us back over to our Blackboard. And I'll actually write out then the factors of 105. So 1 times 105. 2 didn't work. We had 3 times 35. And then 5 times 21. And 7 times 15. So you're more than welcome to use that calculator, or use your calculator to help you find those greatest common factors, especially with these really big numbers that are showing up in here. And we can see ones where these numbers are even larger than 105, and we'll need to find all of these again as well. So again, our main point of what we're doing, we're trying to find the greatest common factor. So what is the largest number that evenly goes into 14 and 70 and 105? But as we're reading through these, you can see, okay, so 14 and 70 both have 14, but 105 does not, so I cannot use that. Okay, so what's the next number down? What about 7? Okay, well, 14 has 7, 70 has 7, and 105 has a 7 in it. So based on that, the greatest common factor for the numbers is going to be 7. So we have our numbers figured out. Now we need to determine for our variables, what is the greatest common factor between all of the x's that I have. I'm seeing I have an x cubed, x squared, and an x. So what is the largest one that all three of these have in common? And again, we could expand these out if we wanted to. We don't have to do that with our little trick of which x has the lowest exponent attached to it. That's going to be this guy. It's got an invisible 1 that's hanging out up here. So x cubed, x squared, and x to the first. The greatest number of x's that these three terms have in common is 1x, or x to the first power. So the greatest common factor for this entire problem is going to be 7x. We always list the factors multiplying together, the numbers, the variables, all of it. Let's take a look at our last example. So we have 9m to the 5th, n to the 2nd. And then we have 12 m to the 3rd n. So again, we're trying to find the greatest common factor. So I'd recommend work with the numbers, then the m's, and then the n's. So listing the factors of 9, listing the factors of 12. As you go through this process, I'm just listing these things off for us. As you are going through this process over and over again, you do not need to list all of the factors in this method, in this way, if you can figure out the greatest common factor in your head or in some other method. I'm just presenting this as, I think, one of the more straightforward ways of finding the greatest common factor. You don't have to use it. It's your choice. It's your call. So looking at the numbers, what is the largest factor that both of these have in common? 1 works, 3 works, 4 doesn't, 9 doesn't, 6 doesn't. So it looks like our greatest common factor is going to be a 3. So that's for our numbers at least. Then I'm looking to my m's, saying what is the greatest common factor between m to the 5th and m to the 3rd? Well, the most m's that they have in common is m to the 3rd power. M to the 5th has 2 extras, but m to the 3rd doesn't. So the greatest number of m's they both share is m cubed. Then looking at the n's, I have n squared and n. The largest one that they both share, the largest exponent that they both share, is just n to the 1st power. So all I can list out for my n's is an n. So the greatest common factor between both of these terms is 3m cubed n. I can't do anything else from there. So this is one of the ways that we can go through and determine the greatest common factor between 2, 3, 4, 5, however many different expressions we're working with. This is a crucial part when we go into our next part here of actually factoring with the greatest common factor with polynomials. If we do not have this down, the rest of these problems are going to be monumentally more difficult. It's pretty amazing, all things considered, I think. So again, this is just a process that you can use. You do not need to use this one all the time. If you look online, I think there's you can just do a quick Google search, factoring with the greatest common factor or finding the greatest common factor, and I'm sure you'll find any number of other methods that people have come up with to find this. I'm indifferent as to which method you would like to use. You'll find the same greatest common factor, you should at least, with any of these methods. Okay. Doing another one, we're actually going to do another one when we get into our next part of what we're doing here. So this is a stepping stone for everything we're about to do moving forward, because our future examples are going to be heavily dependent on finding the greatest common factor. So we will see more of these. I'm going to jump us back over to our notes. Oops, notes, not calculator. Okay, so, oops, there it goes. Okay, so factoring the greatest common factor from a polynomial. So we're given some kind of polynomial. It could be a binomial, trinomial, could have 4 terms, 5 terms, 10 terms, whatever. Factoring the greatest common factor from a polynomial. So we are going to find the greatest common factor with all of these again. So we'll see more examples of that. So first and foremost with our process, this is, again, optional one. You could find others online, but this is the main one that we're going to be working with, at least for this section right now. First and foremost, find the greatest common factor of all terms in the given polynomial. We absolutely must find this. If we don't have this, the rest of this all falls apart. So this is kind of an optional one you can do, but rewrite each term as a product using the greatest common factor. Meaning we're going to basically break this thing down into our greatest common factor times something gave us our original problem. This can be done mentally. It's an optional one if you can. It's your choice on how you want to do that. And then use the quote-unquote reverse distributive property to factor out the expression. Meaning I'm going to take that greatest common factor that I found, our first step, and I'm essentially, lots of air quotes here, dividing, quote-unquote, each of the terms by that greatest common factor. The difference being is we are still going to include and actually have the greatest common factor written out in our final answer. We're just going to see a bigger, longer mess of things written out. Essentially like a problem that we started with in chapter 6. So it's this polynomial times this polynomial or something to that effect. And we'll see examples of that here shortly. And you can check your answer then by multiplying the factors together if need be. So just multiply everything out. If I get what I originally started with, bam, I've got the right answer. I'm good to go. So we'll go through 4 examples with this. And again, if we're asking about more examples with greatest common factor, we're doing that in all 4 of these. So we're going to see more examples of it. So jumping us over to our Blackboard. Why is this thing? Sorry, computer's giving me. There we go. Okay, so our first example that we were working with, we were told to fully factor the following polynomials. And we're starting with 18a minus 36. Now, once again, my goal here, first and foremost, I need to find the greatest common factor of all terms in the given polynomial. When we're doing this, we do not necessarily need to keep track of the negative in here. It's not essential all the time. we are just going to look at 18a and 36 to find that greatest common factor. Now, working with the numbers, saying I'm going to put this off to the side here. So just working with 18, just working with 36. We're going to list the factor pairs of each of these numbers. And again, as I mentioned with the previous ones, and I'll say it again, you do not need to do this step if you know the greatest common factor numerically by looking at these things. Some people can, some people can't, that's fine. Whatever works best for you, figure that out and then move forward with it. So we're saying, okay, what is the greatest common factor that these things both share? Meaning, what's the largest number that evenly goes into 18 and also evenly goes into 36? As I'm looking at it, I'm seeing an 18 is the largest number in both. So the greatest common factor, at least from the numerical part of things, let's write that out. Greatest common factor is 18. Let's look at our variables then. I have an a in the first term, and I have no variables in the second term. Looking at 18a, and then just the number 36. So again, the greatest common factor with variables is the one that has the least of that specified variable. So our first expression, first term, has an a. The second term has no a in it. So they have no common factors of a within them. So my greatest common factor for this entire expression can only be 18. And that's perfectly fine. Sometimes we'll find a factor or greatest common factor that has a variable. Sometimes we won't. It'll just depend on the problem. So now, let's go with this. So in our, I think it's our second step, and again, this is somewhat of an optional one, rewrite each term as a product using the greatest common factor. So 18 times what gives me 18a? Again, just rewriting my first term. Well, 18 times a is going to give us that. And then 18 times what gives me 36? That's going to be 2. Again, this step is optional. You don't need to do this one, but I think it helps to see in our factoring process. Then, step 3, use the air quotes reverse, air quote, distributive property to factor out the expression. So we're seeing our greatest common factor right here, and we're going to pull this out front. So what does that look like when we have a result? We're going to have 18 out front. And what's left over? I have an a for my first term. Keep the sign. And 2 for that second term. And from here, we have just fully factored this expression. So again, big emphasis on the air quotes reverse distributive property that we did in our second step here, our second line of work. Now, you do not need to write things out like we did here and like we did here, where it's a product of two things multiplying together. If that's helpful to you and you want to use that, great, go for it. But it's not something that I am requiring. I'll show you guys another way you can think on it with our next example. So we've got a few of these that we're going to go through. Okay, so we're working with 5x squared minus 25x plus 15. Okay? So I want to find the greatest common factor. I mean, what is the largest number that goes in, or largest factor that goes into all of these things? So our greatest common factor. And again, off to the side, we can list the factors of each of these numbers if we want or we need to. So list those out here. Oops, 3 times 5. Okay. So I'm finding what is the largest number that all of these are going to share. And it's looking like they all share a 5. So the greatest common factor between these 3 terms is going to be 5. Then look to the x's. One has an x squared, one's just an x, and one has no x in it. I can always default to using the one that has the least numbers of a variable inside of it, and that's what I can use. Okay. So we have our greatest common factor, and now I'm going to show you guys another way that we could think about going through and factoring out that 5 from all of the terms. And I went through in the first example how we can write everything written out as a product with the greatest common factor. There's nothing wrong with that. So I'm going to show you guys another way that you can go about doing this, at least thinking about it potentially. I was saying, okay, well, I'm starting with 5x squared minus 25x plus 15. Now I'm going to be factoring a 5 out from all of these terms, and I'm going to be having something left over inside that. So if you're going to do this process, I would say write out the original problem in a line like we have here. Directly below it, write it out as 5 and a parentheses because we're going to have everything that's left over inside here. And what we're going to do for ourselves is say, what happens when I have 5x squared and I divide out a 5? What happens when I have 25x and I divide a 5? What about 15 and I divide by 5? Because that's essentially what we are doing by bringing a 5 out from each of these terms. So 5x squared divided by 5, I'm just going to be left with an x squared after that. 25x divided by 5 is going to give me 5x. And then 15 divided by 5 is going to give me a 3 left over. But again, if we're going to use this method, make sure you have this guy written out front. Because while we are, yes, dividing, air quotes around that, each of these terms by 5, we're actually just factoring out a 5 from the original expression and writing our new answer in this form. So we get this as our final factored form of the original problem. So again, on the homework or on the test, and we're seeing 2 ways of factoring this thing. Our first one has us writing each thing as a product and then kind of reverse distributing that out like we did here. Our second optional method is to say, okay, list every single term and then divide each of those terms by that greatest common factor, and then just list the results inside the set of parentheses with that greatest common factor out front. Either of these are perfectly acceptable. It's your choice on which one you would like to use on the homework, on the test, but I don't care. Use whichever one you are comfortable with. So take a look at another one. Zoom this in here a little bit. Now I'm also looking at our time, so I'm going to jump ahead to the fourth example here. I think that's the one that has the most going on with it. So our fourth example from the set has us working with 3x cubed minus 6x squared y plus 9xy squared. So again, the first thing I need to do, I need to find the greatest common factor between these 3 terms. So let's work with the numbers. And we'll do this one, we'll figure out this one a bit more mentally this time around. So what is the largest number that evenly goes into 3, 6, and 9? And for this, the greatest common factor for the numbers is going to be 3. You're welcome to go through the table or set up and make a table for yourself if you want to. I'm going to try and go through this a little bit quicker though. So our greatest common factors for our numbers is 3. Let's look at our x's. I have an x cubed in the first term, an x squared in the second term, and an x in the last term. So what is my greatest common factor with the x variables? Well, it's going to be the smallest one. That's just going to be x. So I add on to my greatest common factors, now 3x. And then I'm looking to my y's because I have some y's showing up in here. The first term has no y's in it. The second term, the middle one, has 1 y in it. And the last term has a y squared in it. So I still have to use the smallest numbered y that's in there. And the first term has no y's in it in any way, shape, or form. So based on that, I do not have a greatest common factor that will include a y in it. And that's fine. Sometimes we might include y, sometimes we might not. It all depends on the problem that we have been given. So I'm going to use that second method that we use to factor this thing out because I think that's it's a slightly more intuitive one. So I'm rewriting expression that was given to me. Directly below it, I'm going to write in my greatest common factor in a set of parentheses. There we go. And then I'm going to say I'm going to take my original term, original expression, and divide each term by that greatest common factor. That's essentially what's being brought out front over here. So 3x squared, or 3x cubed, divided by 3x. The 3's will cancel, and I'm going to be left with an x squared. Oops. Get the color correct here. X squared left over for the first term. For 6x squared y divided by 3x, 6 divided by 3, it's going to give me 2. X squared divided by x, that's just going to give me an x. And then nothing is happening to that y, so it's just along for the ride. Looking at the last term, I have 9xy squared divided by 3x. So 9 divided by 3 is going to give me 3. X divided by x is just going to give me 1, so those will cancel entirely. And then the y squared, nothing's happened to that, so I'm just going to leave it as y squared. So now I have just successfully factored that original expression. Okay. So this is how we go through and we factor a polynomial using the greatest common factor. Okay. So I'm going to jump us back over to our notes and we're going to go through the last part that we have for this section. So the last thing we're going to do, I'm going to go through this, is factoring by grouping. So we have factoring with the greatest common factor, and now we have another method that we're going to go through, factoring by grouping. So 2 ways we can factor these expressions. The nice part about factoring by grouping is it's a very, very specific instance when we have this showing up. And we're actually going to see this in, I think it's going to be 7.2, or it's another factoring method that we learned in 97. But this is a pretty specific one on when we are going to be using it. But our process with this, group terms with common factors. So essentially we're going to look at a string of stuff and we're only going to look at specific terms within that. We're going to think of it as grouping them together. We're going to factor out the common factor in each group. Again, some of this might sound a little like, well, what do you mean by group? What do you mean by that? We'll go through some examples of this to make this make a bit more sense. The idea behind it is factor out the common factor in each group. So I'm looking at parts of this thing. Factor the common factor from the expression. Should be common, not command in there. So we're basically doing factoring by a grouping. It ends up basically doing that twice. And when we do that, we're going to then check our answer by multiplying everything through if we want to make sure we have the correct final answer. In a fair amount of these instances, specifically with factoring by grouping, if you can factor out a negative between two terms, do it. And we're going to see that show up in several of our examples here, so we'll show you what that exactly looks like. So we're going to go through a couple of these, again, time permitting with this. We'll go through a couple examples with this, because again, it's very, very niche in when we're going to be using it, but the process is extraordinarily mechanical and very, very predictable to see with where these things will go after a couple examples of it. At least I think that is, which is what's nice about it. So we'll jump on over to our Blackboard. Move this down here. Separate this out. We'll take a look at this. So we're factoring by grouping. So our first example that we have is we're working with x squared plus 2x minus 5x minus 10. Now we're going to be seeing factoring by grouping showing up when we have an instance like this. We have a 4-termed polynomial showing up, and the terms in the center are common factors. So factoring by grouping, again, very, very, very specific uses when we can work with this thing. It's actually encompassed in a method that we're going to use. I think it's in 7.2. If not, it's definitely in the 97 material or the next class material. But for now, we're going to go through again by the factoring by grouping. So what I like to do with this one as we're going through this for the first time is say, all right, I'm going to rewrite my problem for myself. But as the first part is telling us in our first step, group terms with common factors. So my recommendation with this as you're going through this is think on, I'm just going to look at these first two terms as a group, signs and all. I'm then going to look at my last two terms as a group, signs and all. I'm going to ask myself, what is the greatest common factor for this first grouping? What's the greatest common factor between x squared and 2x? Well, the greatest common factor for those is just going to be x. What about the last two terms, this negative 5x and this negative 10? Again, trying to find that greatest common factor. In this instance, the greatest common factor they both have is a 5. We're also noticing that both of these numbers are negatives, so we can also bring out a negative 5. So when we do that, we would go through and use our previously learned method of factoring something out with the greatest common factor. For the first pairing of terms, I would get x times x plus 2. Again, using the method that we just went through to get to that answer. I'm going through this a little bit more quickly only because I'm looking at our time. But the process is the exact same with our previous examples that we just went through. With our second group, the greatest common factor is negative 5, so I'm putting that out front. And then what's left over in each of these terms when I divide them by negative 5? Well, the first one's just going to have an x, and the second term is going to be a positive 2. Now from here, we're saying, all right, well, I've done the first part of grouping, or factoring by grouping. Now I need to do a second round of this. And I'm saying, for this next one, I'm seeing, looking at this term and looking at this term, what is a factor they both have in common? And for both of these, they both have an x plus 2 in common. So the greatest common factor here is x plus 2. This guy here, that guy there. So if I were to factor those out, meaning if I were to bring those out front as a single term, I would have an x plus 2 written out front. And when I did that, what would be left over? It's going to be x minus 5. I can't factor this thing out any further. I'm done. A really big giveaway as we go through this process and we're finding our greatest common factor and we're factoring things out. When we get to our second round of factoring, which we should be getting to here, we should always be finding, we're going to have a binomial as a greatest common factor. This x plus 2 worked out. It was in our first term. It was also in our second term. So if you are trying to wonder, you get to the understandable, difficult part of, do I factor out a negative with this thing or do I not? In your line after it, if we don't have the exact same thing for one of our factors, like we have here for binomial, then we may need to go back and factor a negative sign out from this. So taking a look at this over here, another example with this. So take a look at number 2. So if y squared plus 4y minus 7y minus 28. Oops. Come on, mouse. There we go. So again, factoring by grouping, I like rewriting the thing and then doing some kind of an underline or something to tell myself I'm working with this group and then working with that group of numbers. So I'm telling myself I'm working with the first grouping is the first 2 terms, and the second grouping is the last 2 terms. So now I find what is the greatest common factor between the first 2 terms in this expression. Between y squared and 4y, the greatest common factor is just going to be y. Between our last 2 terms, we have a minus 7y and a minus 28. So in this instance, let's say we determined, okay, I'm just going to have a greatest common factor of 7, not use a negative 7 in here. So what would happen if we did that? Well, in our next line, bringing a y out from our first 2 terms, what's left over? Y plus 4. Look in our last 2 terms. If I factored out a positive 7, what's left over? Well, I have a negative y minus 4. And now in this line of work, we should be getting a binomial that is the exact same to one another, signs and everything. But if we're looking at our second one, we're noticing, well, okay, the values are the same. One's a y and one's a 4. But the signs are different from one another. They're the exact opposite of each other. So this, when it happens, and it's very understandable if or when it does, when this happens, this is our cue to go back one line before this and say, all right, I need to change the greatest common factor that I used. I need it to, instead of being a positive 7, I need it to be a negative 7. So let's adjust our answer accordingly. And if you have to do this, this is not uncommon. It's a very regular thing that shows up. So instead, now if I factor out a negative 7, what would I get instead? Well, I'd be getting a y, and then I'd also be getting a positive 4 there. Again, going through that factoring process that we went through with our previous examples. And now suddenly I have y plus 4 and y plus 4. Fantastic. This is where I want to be. I want to be able to see, oh, these binomials are the exact same in both of these terms that I'm working with. So now, what is the greatest common factor between the first expression and the second expression? It's this y plus 4. Not GOF, GCF. There we go. So if I bring that y plus 4 out front, what's left over? Y minus 7. It will write for me. There it goes. Yeah. So this is our general process for going through and factoring by grouping. We should always be finding after the first round of factoring that we do. We should always be finding our second step, our second round of factoring, that we should have a binomial that is the exact same. In our first example, it was they both had an x plus 2 in them. In our second example, it was a y plus 4. Sometimes there will be positives, sometimes there will be negatives in there. It doesn't matter. But we want to make sure that the binomial, in that starred step that we have there, is the exact same. The values, the signs, the variables, all of it. If we don't have that, then we may need to go back a line before and see, do I need to factor out a negative? Will that make the signs correct? And that's generally the most common one that shows up with these. Okay. So this is everything for the 7.1 material. I'll end our recording here.